we talked about what on Monday? We're going to start with a little back and forth. What did we do on Monday? Yes, thank you. Sampling distribution. Good. What does sampling distribution mean? Whole lot of nothing. And you paid for it. How do you feel about it?
Oh, we're trying to get the correct sampling from.
Not correct sampling. Sampling distribution, what is it? Okay, maybe start differently. Which chapter are we on?
Chapter 4.
Yes, excellent. And chapter 4 says we are going to move away from picking a value out of a population and comparing it to a population. We're going to take a sample out of a population, right? And we started talking about sampling distribution, which means we are talking about taking a sample out of all the possible samples. Yes, we did that. We said that if we want to take a sample of size 5 out of 28 members of a population, we have to consider 98,000 samples. Yes? Yes. But because we didn't want to deal with checking 98,000 samples, picking one sample and checking all the other ones, we realized that we can equate the average of sample means to the population mean, right? And we can equate the standard deviation of the sample means to population standard deviation divided by the size of the sample, right? And what came out of this discussion is the central limit theorem. The central limit theorem says what? There's three things to it. One says, hey, if we take a large sample, or large enough, which is above 30, right? Sample above 30, we don't care how the population looks like. We know that the samples, for example, the means of the samples we're going to be taking, are going to be normally distributed. So suddenly the 98,000, for example, 98,000 samples that we could possibly take from the population, suddenly all of those are normally distributed. If they are normally distributed, we can do something about it because we dealt with normal distributions, right? We took normal distribution and we turned it in standard normal distributions and we dealt with it because we know a lot about standard normal distribution. Case 2 was slightly more tricky. Case 2 said, hey, if we take a smaller sample, 30 or below, right, a small sample, then we need the population to be normally distributed for the sample means to be normally distributed, right? So if the population is normally distributed, the sampling distribution is normally distributed. That was case 2. And case 3 said, we don't know what the population is. We have no clue. We're taking a small sample, and right now it's one of those, I don't know how to do it, right? So we have 3 cases. Big sample, and we don't care. We just get it done and done. We don't worry about it. Small sample, and we need to have a population that is normally distributed to be able to do things. Or small sample, we don't know and we cannot do it. And so, before, when we dealt with, and by before I mean a couple lectures ago, right? Before, when we dealt with standard normal distributions, what was the one thing that we always needed? I said standard normal distribution. You said the z-score. Cha-cha-cha. Cha-cha. The z-score. And the z-score had what formula? Okay. How about behind? Divided by the canon. Canon is always on the bottom. Okay. So we get that, right? And this was for an individual beta value. X. Everybody agree? Good. So now is what? Now we are no longer talking about a single data value, right? Now we're in chapter 4, we are talking about a sample. So we still have our z-score, and what? We no longer have x, so what do we have instead? X bar, right? We are not looking at a point, we're looking at an average of points, right? Average of it. Minus, here we had the average of all the points, right? That's the mean of the population, so that's the average of all the x's. Well, in our case, we don't have x's, we have x bars. So we have the average of all the sample means, right? This is the average of all the data values, here is the average of sample means. And divided, well, we no longer have standard deviation of all the points in the population, we have a standard deviation of the sample means, right? We turned our population into a population of samples. There's a problem with this equation. What's the problem with this equation? To get this, right, and to get this, we would need to create the sampling distribution. And as we already realized, the sampling distribution has a really good chance of being way bigger than the population to begin with, right? So it's not very fun to collect all the samples, calculate the mean for each one of the samples, and then average all those means. It just seems like a lot of work, right? But in our discussion, we realized that, hey, the average of all the sample means, right, of sample means, equals to the population mean, or the population average. And standard deviation of the sample means equals to standard deviation of the population divided by the size of the sample. Right? That was central limit theorem. I know. You missed it. We're getting there. Just squint your eyes and deal with this and this to this. Do that later, right? It's just another formula. Right now it's another formula. There's a reason why we're using it, but we're going to get to this in a second. And I'm going to do an example to cover it, right? And so our z-score turns out to be x bar minus mu divided by sigma divided by square root of n. Okay? So now we have a new z-score. Population, sample size, and sample mean. All of those are easily accessible to us. So this is for an average of a group of values. Yes, we must. We must. There is no way we're moving anywhere without doing an example for this. Okay. I'm going to shift this over. I'm going to leave it on the board. I'm going to shift it over. All right, this is an example. This example has two parts to it. So we're going to try to solve both of them one after the other so we can see, compare the differences. So the question, so the example looks like the following. A population of man have a mean of 172 pounds and standard deviation of 10 pounds. So that's the premise of the equation. Now here comes part A, part B. Part A says find probability that a randomly selected man will weigh more than 175 pounds. So find probability that a randomly selected man will weigh more than 175 pounds. Part B is find probability that a group of 20 men will have an average weight of more than 175 . And we have to add that assumed weight is normally distributed to satisfy the central limit theorem. So those are the two questions. Can we solve A? The answer is of course we can. We did it 2 weeks ago. We are so good at it. So let's solve A. How do we solve A? Well, step 1 is what? Z-score. So Z-score is x minus mu divided by sigma. Why am I using x? Because I'm looking for one selected man, randomly selected man. So that's why you have an x versus x bar. What's x? 175 minus 172 divided by 10. 3 divided by 10, 0.3. Okay. What's next? What's step 2? What's step 2 when solving problems with z-scores? Oh, guys. Step 2. Draw the goddamn picture. It's always about the picture. You're gonna love it because homework 3 and 4, the rest of the 3 and 4, it's all with pictures. Like almost every problem requires you to draw a picture. Almost everyone. There's some exceptions. So let's draw the picture. Behold a beautiful standard normal curve. Freehand. Lots of practice. Where's point 3? What's in the middle? What's right here? No. 0. It's a standard normal. So mean is 0. So this is 0. So 0.3 will be here. And now which area are we looking for? And by area I mean probability, which by mean area, which I mean probability. Which area am I looking for? Yes. So I'm looking for this. Okay, let's find it. It's over there. You're looking for that. Yes, you're looking for that. Oh, hello. Anybody needs a table? Don't worry about it. Oh, you have it? Okay. Good. Just in case you forget, I always have one extra. Okay, so how much is it? Which area? That one? You sure? Look at the picture. Yeah, hello. You're right about the number, you were wrong about the area. This area is the one that is 0.6179, right? Or something. Yes, why? No, 2 is not the answer to y. That's not why we are subtracting from 1. No, this is how we are finding the other side. Why are we finding the other side this way? Because this is a standard normal curve, and we force the area or the probability underneath it to be 1. That's why we can do this. Right? This is how we do it, is to find the other area. But why is because this plus this has to be 1. So this is 1 minus 0.6179, which comes out to be 0.3821. Right? And the answer is the probability of randomly selecting a man that weighs more than 175 pounds is 38.21%. Okay. Doable, right? You're slightly heavier. You're looking for somebody slightly heavier than the average. The chances are slightly less than 50%. Makes sense? We're happy. Let's do the other one. The other one, here comes the great part about chapter 4, is you can hear that you probably need to use this versus that. It says a group of 20. The 20 is important, right? It's talking about an average weight. Right? All of those little things suggest that we are talking about a sample rather than a single value. Well, but then again, we solve all those same problems the same way. So z-score is x bar minus mu divided by sigma divided by square root of n. What's x bar? X bar is mu. So x bar is 172? 175. We are looking for a group of 20 with an average of, right? So x bar is 175. Mu is 172. Standard deviation is 10, and then size of the sample is 20. Okay, how many of you are really good with the calculators? Okay, people that raise their hand, you need to listen extra carefully because you're the people that will have the common mistake. How do we solve this using a calculator? There are several ways to do it. One is you plug in one thing and then you press enter and then you write it down on your little notebook and plug another thing and press enter and do it. Which is a great way Just, I know most of you won't write things down. You won't be precise. I seen your exam. That doesn't happen. So this is how you do it. You go 175 minus 172 first. Then you're dividing by a fraction, which means that you're multiplying by its inverse. That goes square root of 20 divided by 10. So how do you plug it into a calculator? You plug in 175 minus 172, and you press enter. Then you go multiply, or let's go divide by 10, and you press enter. And then you go times square root of 10, and you press square root of 20, and then you press enter. Or if you want to play with parentheses, you plunge in 1 times the other. But this is how you do it very efficiently on your calculator. Plug in 1, enter, another, enter, another. Or you can do it this way. Open parentheses, those two, close parentheses, times this, right? Or divided by parentheses. But I know for a fact, the limited sampling data I have about students and calculators, you guys don't like parentheses. So this is how you do it. First one, enter. Second one, enter. Third one, enter. And what are we getting out of this whole thing? Is everybody happy with getting 1.34? Yes? Yes, okay. All right, so how do we do next? What's next? Yeah, pictures. And again, let's say 1.34 is somewhere here. Now, where do I care where you put 134? No, as long as it's on this side of the 0. Now, how big is that area? How big is this area? Let's start simple. How big is this area? Right here. Do you have a table? No, it's okay. I'm just checking. I want to make sure. Look, guys, reading Z-score tables is paramount because from now on till the end of the semester, with very few exceptions, we're just going to be making love to the table. To the point where I'm considering printing an extra copy because the ink will be wearing out by the time we're done with it. So if you don't know how to read the Z-score table, you don't know how to deal with it, hands up now. Don't be quiet. Uh-huh. So this one is yes, minus 1 minus 0. So probability is 9%. There's 9% chance of selecting a group of men that will have an average weight of more than 175 pounds. Does it make sense? Yes, question.
So do we have to look at this one before we look at this one, or can we just look at this one?
If you are capable of looking at minus 1.34 and knowing to flip it, I'm golden. You make a mistake, I'll be like, ha ha. Or I'll be rather than, ha ha. right? It's up to you, right? If you understand the symmetry and you're good with the table, I'm happy with either way. Any other questions?
Oh, can I see the calculation?
Yes.
Oh, okay, divide by 10. Square root. Right. Are we looking at 20 or we're looking at 10? Sorry, I got a little bit confused for the table.
For the table, you're looking at this. You're looking at the wrong table, my friend. This is not binomial distribution. This is standard normal distribution.
I didn't know we had more.
Remember this table?
Yes.
Right. So this probability is 1.34. Which is
I got you.
do a couple practice ones. If you get stuck, let me know. If you type in z-score probability handout kind of thing in a search engine, you should be able to get questions with answers with, to practice with. If that's still a problem, shoot me an email. There's a couple of people here that are pretty good at it. She's volunteering. I'm volunteering you as tribute to help with z-score tables. Okay. So now, the main thing from this is it's easier to find a single individual that has a statistic than to find a sample. Right? It's easier to find one person. I mean, assuming you're all poor college students, so you have somewhere between $1 and $20 in your pocket of change, maybe a couple quarters laying around. So if I said, hey, I want to randomly pick one of you that has $15 or more, the chances of that would be small but not impossible. But if I said I want to pick randomly 10 of you and I want on average the 10 of you have $15 or $150 total, the chances of that are way slimmer, right? Because you have to pick an average. Okay. Right. I'm assuming we want more, so let's do more. The basis for hypothesis testing, or in our case, the decision making in statistics, comes from a very simple rule. And the simple rule says rare event rule. The simple rare event rule, the rule states pretty much once a cheater, always a cheater. It says if under a given assumption the probability of an event is really small. And we're going to try to define really small later in the lecture. Then that assumption is probably wrong. Yeah. The chances of me dying because of a meteor strike are really, really small. So me assuming I'm going to die because of a meteor strike is probably wrong. That's what it means. Right? This is the basis for most of the hypothesis testing we're going to do. Because we're going to look at probabilities and say, hey, there's a really small probability of something happening, that statement is probably wrong. Or probably insufficient. Right. So let's do an example. An example is, how many of you want to work in health policy or health administration? Right? The hospitals are everywhere. So if you're a hospital administrator, right, you have to collect data. And now that everything is on the computers, you can actually randomly pick up samples of data from the computer and take a look at it. So let's say you're at a hospital situation. So the example is the following. The example is as following. Body temperature has an average of, what is it? People that have small nieces or nephews or kids know the answer to that question. Everybody else is like about 99. So people that have been around a while have the answer to the question. So I want to know if this is your first year of college. I just ask you this question. If you're a freshman, no clue. Sophomore, no clue. By junior, senior year, especially with people that have been to workforce or have kids, 98.6 is just kind of like, yep, done. And a standard deviation. Oh, nobody. Okay. 0.62 degrees. Which means that you have over 99.8 degrees. That's unusual, right? That's unusual. And if you have below 97.4, that's unusual. Right? So 2 standard deviations. So we know this. So in your hospital, a sample, and by sample I mean a random sample, of 106 patients was selected. What is the probability that the average Now here comes the beauty of dealing with people that did statistics and people that didn't do statistics. People that didn't do statistics look at 99, look at 98.6, and they go like, well, it's the exact same thing, right? A little warmer. Who cares? It's a hospital. There are 6 people, right? In theory. Should we panic? No, exactly, right? But let's do the math part, right? Because this is the part where we should be worried. If you are administrator, right? You want to watch things like this. 106, that's a big sample. So you would expect it to be very, very close to the population, right? And if the population is 98.6, 99 could be too far, right? So let's calculate it. So how do we do those? Well, we're doing the one for individuals or for the sample? Right, sample, we have 106 people. We're talking about averages, so we're talking about sample. So that's x bar minus mu divided by sigma divided by square root of n. So in our case, that's 99 minus 98.6 divided by 0.62 divided by square root of 106. Are we worried that the patient's temperature is normally distributed, or are we not worried? Should we worry? Everybody's on the calculators. Guys, conditions. Should we worry if the patient's temperature is normally distributed or not? Why not? No, but I'm asking if it's normally distributed. Yeah. Oh, this right. Remember when we talked about the weight? I said assume the weights are normally distributed. Here I don't say it's normally distributed. You cannot do z-scores unless it's normally distributed. But central limit theorem says if the sample size is greater than 30, we don't care. This is greater than 30, right? So you might get a question on a quiz next week, perhaps, giving you a problem that I will say, hey, 27 people got checked for something, right? For size of lungs, for example, and it won't say normally distributed. We'll be able to do this question. Exactly, right? So I'm not saying there will be a quiz next week, and I'm not saying it will ask that specific question. No, I'm saying, right, there's a reason why I gave you pieces of information like this. Okay, so now that we checked, we're good. We're solving this. What are we getting? You plugged it in wrong, I'm assuming. If you're doing parentheses, do top parentheses divided by bottom parentheses. Otherwise, do the enter thing. You're getting it. Got it? Cool. You got it? All right. Let me help. You need a second parenthesis here. Here parentheses. So yeah, divide by parentheses 0.62 divided by square root of 106 close parentheses 1 close parentheses.
Okay.
Try to. You got it? You got it as well? Okay. Let me know if you get the same numbers I do. Okay. So, should we worry? Why? Okay, so the probability is high. How high? How low? Anybody want to take a wild guess how big that number is? It's not even honest, right? Y? Oh, sorry, that's P. That's the probability, just in case you wonder. I use the calculator. I had to use a calculator to do this. Now, will you be able to get this on your own? Yeah, sure. Do I want you to? No. When you get a z-score of positive 6 or negative 6, that's very close to 0 and very close to 100, right? So there's two ways. There's one way that I would like you to deal with questions like this. So if you have a z-score, bigger than 3.5. Because 3.5 you have on your table, right? Or you have 349? 9. So bigger, write this. Then say that the probability equals to 0.9999. Right? If you have a z-score smaller or equal to 3.5, to negative 3.5, then say probability equals to 0.0001. This will tell me that you know it's not 100% or 0%, right? And it will tell me that this is beyond what's in your table. Although if you have a z-score of 6 or 6.6, if you want to put 5 more 9s behind it, I'm okay with that. Or, a bunch of more zeros. Like at this point, artistic creativity takes charge, put a couple zeros, couple smiley faces, maybe a poop emoji, It's kind of let it be. Because at 6, the chances, right? The chances of things happening like this are very, very small. Now, here's my question. What is this probability for? I wrote you a probability. I told you it's 0.9999. What is this probability of if you had to take a wild guess? Yeah, no, that's not what I'm asking. What I'm asking is, how many of you drew the picture and tried to figure out where this is? So let me draw you a picture. Now you're just saying words. Where is 6.6? Six 6.6 is about here. Which part of the graph am I looking for? So I'm looking for this. This fine. This little part, and I'm telling you this is probability for that little part. Right? So be careful because everybody they saw 6.6 and everybody's agreeing with me. It's 0.99999999945. You all agreed to me, right? And yet nobody checked the conditions of the question, right? This is one of those another kind of examples that might not show up eventually on a quiz or a homework or somewhere or exam, right? Which I'll give you everything. And the question is, can you put it together, right? If you don't draw the goddamn picture, you're gonna run into problems. If it was -6 up, yes. Or if it was +6 down, yes, then that would be about this. This little bit.
Also, like a number less than
99 or less, then yeah. Everybody should. The average of 106 people should be 99 or less. Right? The probability that in a hospital which says the average is this and standard deviation is this, to pick 106 people, probability of picking 106 people that have a high fever is that. Somebody would show me this. I'm saying that they're measuring the temperature of a hospital that's on fire. Yeah, your body is on fire. I'm going to stick a thermometer into you and calculate that. Okay. Conclusion, we draw the picture. Okay, next. Point estimate. What's a point estimate? Point estimate is a single value that we use to approximate the population. Just like most of Europeans assume Americans are just like the president. Point estimate. Point estimate for America is Trump. Why? You think he's a bad point estimate? Are you sure? I mean, look at it this way. Think about an average American, the way you would think about an average American, and then consider that 50% of people around you are lower than that average. Well, that's what average means, right? It's right in the middle. Well, now we can just pick and choose, right? So that's point estimate. So we talked about means, right? We have X bar and mu. Let's talk about proportions. So we use P as the population proportion of success. Right? Binomial distribution should come to mind. So P hat would be what? And Q hat? Yes, sample proportion of failure. My previous class said it's sample proportion of not success. I know this is politically correct, but no, in this case it's success or failure. You're in the first place, and there's no second place. There's the first loser. There is no, soft middle. This is sample proportion of failure. Okay. How do we define proportion? Proportion of success. How would you define proportion of success? Sure. How do you get the percentage? Sure, but so if I consider P hat, what would be on top? On top would be number of successes, and on the bottom would be number of trials. Yes? Question 9, exam. Right? We had that. No? Yes, we did. We had the next. Right? Proportion of females in this class. It's the number of females divided by everybody who's in this class. Right? Success versus number of trials. Okay, next question. P hat plus Q hat. How much does it equal? 1, because either a success or a failure. But that also leads us that Q hat equals to 1 minus P hat. Right? So what's P hat? Well, P hat is x divided by n. So this is 1 minus x divided by n. 1, we can change 1 into n divided by n is 1, right? So this is n divided by n minus x divided by n. And so what we get getting as q hat is n minus x divided by n. So just in case you get a problem which has an x and an n, and you don't want to calculate p hat, you just want to go directly to q hat, and that's useful when you're using a spreadsheet to do those calculations. This is a quick way to plug in a formula that will actually do it for you, right? Yeah, for sample proportion of failures. You take everybody minus the successes divided by everybody. Everybody minus the successes divided by everybody. Right, again, if you're working with an Excel spreadsheet to do it. I'm hoping we can spend about a week solving things on a spreadsheet, just so we can do those formulas so you have a baseline for when you start doing big data for work, but for now this. All right, so let's talk about a magician. So example, a magician did a guessing trick. And the guessing trick looks the following. I have an object. Which hand do I have it in? Right? So that's a trick. I have an object. Right? Which hand I'm not a magician. I'm a statistician. I sit there like, that's a 14% to fail, and give me the money. Right? So you do this trick and you guess which hand it is. So we have a magician that does this guessing trick. And that's this guessing trick 280 times. Right? Most magicians have their trick posted on YouTube, so you watch 280 of those same tricks. And he guesses right 123 times. Oh yeah. So my question is, what's the point estimate for the population? So you only saw this guy do this trick. You want to go and see another magician. What are the chances that magician is going to succeed in this trick? Right? What's the proportion of the successes of any magician? What's the chances that any magician that you pick up from the street is going to be able to do this trick? Well, he's the only point estimate you have, right? This is the only thing you know, which means that p hat is the point estimate for the population. And how big is p hat? Well, it's x divided by n, which in our case is 123 divided by 280, which comes out to be about 44%. Right? So if this is the only thing we saw, right? We live in a small town in, I don't know, rural South Dakota, and we have a magician that keeps on doing this trick on the street, and you keep on checking him over, and then you go get to a big town like, sorry? I was going to go with, Madison Creek, Wyoming. Population 724, right? And there's another magician there. What are the chances that magician will go and get the trick right? Right? This is your only estimate. Just like if you assume that all Americans are like the point estimate that people see on TV, which is, Kim Kardashian and Donald Trump. Those are the role models for this country, right? Till you find otherwise, this is what you have. Right? As statisticians, this is what you have. You have one piece of data. So if you've been checking cars and all the cars are failing, having an engine failure after 10,000 miles, the assumption is that next car you're going to check is going to have an engine failure, because this is all the information is. So this is question number one. This is the point estimate, because this is the only one I have. Here's the difficult question, and that's one of those quiz type questions that Mr. N likes to throw around. Is this good? Is this any good? It's 44% guessing any good. Mind you that if I flipped a coin, I have a 50% chance of getting it right. I flip a coin, I'm getting better results than a magician. So is this any good? Is this a good?
Is he a good magician? No.
Well, is this a good? No, I'm asking you if this is a good number.
What's the standard deviation?
Well, you don't need you.
From 50%.
Well, what do you mean 50%? This is the only thing you have. I'm asking you if this is good. This is the only thing you have. The question is, this is good.
No, it's below 50.
Take a vote, guys.
Anything over 50 would be good. It's better than-
So, okay, so there's an argument, logical argument, saying I can flip a coin and make a better magic trick with flipping a coin than this guy. So that's one argument. Second one is 44 sucks for magician. It's not your job to tell me if this number is good or not. This number is good because this is what comes out of the calculations. Even if you don't agree with it, even if you have a preferential treatment for coins versus magicians, you cannot tell me if this number is good or bad. This number is correct because this is what came from the data you have. Very often, when I worked in a research lab, it was very often that somebody got a piece of data and then they decided that they're going to just skew it a little bit. We're not going to count Wyoming for presidential vote because it's mostly goats, cows, and cornfields there. So, per se, most of the people there are not counting, right? Or we're not going to count Florida because it's old people and they're not going to live long enough to enjoy the embarrassment of the president, right? You start putting your own personal skew on numbers. You're no longer doing statistics. You're doing subjective probability, which by all counts is not probability, it's just subjective, right? Sorry? Yeah. Well, it's not math, it's just bias. And there is no bias math. It's either math or it's bias. There's no bias math. There's no middle ground. It's either you're on this side of the fence and I like you and we can talk about grades, or you're on this side of the fence and that was the biggest mistake joining this class, kind of thing, right? The idea behind this is that when it comes to decision making, you have to have two pieces of information. One is, here's the data, here's my calculations, this is what I'm getting. This is my z-score. It's 6.64. That's what I got, right? This is what I did. You gave me, this is what I'm getting for probabilities. This is what I'm getting. That's part one. And part two is what you do with the data. And there's some considerations. We are not going to count people in burn unit for temperature analysis. We are not going to count the tricks when the guy was too drunk in this calculation, right? Then you have to start making decisions. But you start making decisions, you start making assumptions, right? The number is good. This is what you got, this is what you got. There's no way around it, right? There's no skewing it one way, right? This is very famous set of politicians that come in and says, we have data that there's climate change, but we don't have climate change because I can make a snowball outside and bring it inside. Look, it's a snowball. There is no global warming, right? This is a very famous speech, right? Statistics is one thing, data says one thing, decision making, it comes a second. The tricky part about statistics is to be able to say, hey, this is my data, this is what I stand by. It doesn't agree with my observation, doesn't agree with my experience, but unless somebody tells you, hey, you're upper management, you make a decision, if you're just doing statistic correlations, for example, this is what you got. You got 0.44. As far as you can tell, every magician gets below 50% things right. Until you find another one and you have more data to compare it to and another set of statistics. Right? I want to drive this point very much home because it's very common. What we are doing is we're doing simple problems for the most part. But the consequences of your mentality behind those problems is what's going to make you good at certain jobs and what makes you dangerous at certain jobs. Right? How many of you like the fact that we are spending millions of dollars to build the rail outside? And don't raise your hands, I don't want to know, right? But if you really, really hate that project, even though statistically it says that it will be good for the community, you're going to put a bias on it. On the other hand, if you really, really like the project and it statistically shows that it's going to be negative impact on the community, you're going to skew it. We all do, right? Do those genes make me look fat? Is one of those beautiful questions. Statistically, you know what fat means. You know which pair of genes is in that. You know the standard answer is? Honey, it's not your genes, it's your mom's. But as a chemistry joke, you know, it's horrible. I know, I found that one out too. Right? I'm a honest and straightforward person that does science. You ask me a question, I'm going to give you an honest answer. Okay, so this is that. The last piece of information. So we are starting to talk about, we are starting to approach this topic of making decisions. So we should start talking about what is really small, right? Remember when we talked about rare event rule, we said that if the probability of something is really small, the assumption is probably wrong. If probability ends up being below 5%, we can consider it to be small, unusual, and rare. So if probability of something has 5%, the language we're going to use when talking about probabilities like this is that probability is small, as in unusual, as in rare. Now, which one, depending on the situation and how small this number is. If this number is 0.5%, so there's extra zero in here, then we are going to be talking about something that is very rare. Right? When it's 5%, we're going to say, hey, this is unusual. I think that's it for today.